of combining one rotation with another rotation. Now, if the two rotations have the same center, then obviously the result of combining them will just be the rotation by the sum of the angles. But if the two rotations have different centers, then it can be a little tricky to figure out what is the net effect. As you might expect, the net effect is going to be a rotation, but finding the center of that rotation is a little difficult. So let's start with a diagram in which we have this weird looking hexagon, which is rotated from first position to second position by a rotation around the point G, which is actually a 30-degree rotation in this figure. Now we're going to add a different center of rotation at point H and rotate by a different angle around the point H. And we're going to move from this second position to this third position by rotating around the center H with a 70-degree rotation. And I just picked those numbers out of a hat. Now, what we want to explore here is what's the net effect? How do I get from position 1 to position 3 by the application of a single transformation? Now, it looks like it's a rotation. It's not centered at H. It's not centered at G. The challenging part is to find the center of that rotation. It doesn't take a rocket scientist to figure out that a 30-degree rotation followed by a 70-degree rotation is going to have a net effect of a 100-degree rotation. The difficult part is finding out where is the center of that 100-degree rotation, which will take us from the first position here to the third position there. So in order to find the center of that rotation, we're going to start by constructing the line from G to H. And then we're going to construct a couple of angles. The original rotation around the center G is a 30-degree rotation. So what we're going to do is we're going to cut that 30 degrees in half, and we're going to construct two rays starting at G, a 15-degree ray here and a 15-degree ray here, so that both of these angles are 15 degrees. The point of this is that now we've got a 30-degree angle at G, which faces H, and every point on this lower ray will be mapped by that clockwise 30-degree rotation to another point to a corresponding point on this upper ray. We're going to kind of do the same operation at H. We're going to construct two rays at H, but because the original rotation centered at H was a 70-degree rotation, we're going to cut that in half for 35 and construct two 35-degree angles at H. So you can see this is a 35-degree angle here, and this is a 35-degree angle here. The point of this, similarly, is that every point along this upper ray constructed at H will be moved, rotated by 70 degrees to reach a point on this lower ray. And now we've got these two rays constructed at G and these two rays constructed at H. Let's find out where they intersect. We'll label those points of intersection I and J. Now I and J are quite special points here because they are moved back and forth to each other by these rotations. To be specific, if we rotate 30 degrees around G, then the point J will move to the point I because we've constructed this 30-degree angle at G. But if we rotate 70 degrees clockwise, centered at H, then the point I will move to the point J. And that means that if we combine these two rotations, the points will move back and forth. So if we start at J and first apply the rotation around the point G, J will move to I. And if we furthermore apply the rotation around the point H, then I will move back to J. And that means that J is a fixed point of the combination of these two rotations. That is, when the rotation around G of 30 degrees is followed by the rotation around H of 70 degrees, J will move to itself. And that means that J must be the center of that 100-degree rotation that moves our hexagon from the first position to the third position here. So this is how we find the center of a rotation which is obtained as the combination of two different rotations, one about one center and one about another center. I want to point out here at the end of the video that this procedure can fail under certain special circumstances. If a rotation followed by another rotation amounts to a 0-degree rotation of the plane or a 360-degree rotation of the plane, then that's not technically a rotation at all. Now, in some circumstances, that means that it's the identity transformation on the plane, but not always. Sometimes a rotation of 90 degrees about one center can be followed by a rotation of 270 degrees around another center, and the net result is this 360-degree or 0-degree rotation, which can be then either the identity map or simply a translation. So if you should find that the angles of rotation add to 0 or add to 360, then you're looking at a result which will be a translation. And in order to find out which translation it is, you just follow one point, and that'll give you the vector of that translation.